Lecture 21. Let us do this follow-up to Lab 8 and confidence interval, which is a fairly new topic for us. First, the difficult part, regression versus t-test, how to tell them apart. For US crime data and murder counts in Texas and Vermont, what do you use, regression or t-test? Which one makes sense and why? Okay. Let us start with regression. So here we are using regression for in x-axis we have Vermont and in y-axis we have Texas, and the regression equation is given. R square is 0.28 and p-value is 0.000154. So here it means that Vermont's murder count might help us to predict the murder count in Texas. That's what the p-value says. Okay, so let's see what it is written here. What did we learn? Since the p-value is small, we are very certain that there is a connection between murders in Texas and Vermont. Okay, is this a very strong connection? No, since R square is very low. Okay, 0.28 is very low. What does its dot represent? A year. Okay, murder in a year. Conclusion, we are very certain that on average for years when Vermont experiences murder increase, Texas also does the same. Okay, so that's what is given by p-value. And let us look at this graph, and you can see that average murder count in Vermont is way less and Texas is very high. Okay, you can see that the p-value for t-test is 3.33 e to the power negative 24, which is very small. Okay, what did we learn? Well, nothing really. Nothing really. The t-test confirmed the obvious. Since Texas population is much higher than Vermont's, the number of murders in Texas is much higher as well. Thus, the t-test here is not wrong, but it does not make much sense to conduct it. That's all. So here mark this line. Okay, not all tests that could be performed should be performed. So some tests and start procedures are reasonable and some are not. Now let us do task number 1. Upload the flyers customer data. In order to increase the number of customers, your boss decided to try distributing flyers. The data represent the number of flyers as well as the number of customers per given day. Given the data, your job is to perform the appropriate statistical test or procedure and help your boss with decision. So to increase the number of customers, your boss decides to try distributing flyers. So here what our boss is thinking is that if we distribute flyers, then that will increase the number of customers. So we are predicting the number of customers by distributing the flyers. Okay, so that's the case of regression. Here I have opened the flyers and customers data, and here what is the p-value? So let us do the regression. So go to data analysis. We need to predict the number of customers, so that's y range. Okay, and the x range is flyers. Okay, number of advertisement distributed. So that's labels, and click on OK. Thus we get our regression table. P-value for flyers is, so that's very small, which is 0.029. One line statistical interpretation. So what we write down is, since p-value is less than 5%, there is a connection between distributing flyers and number of customers. Okay, so since 0.029 means that's nearly 3%, which is less than 5%. So if we distribute more advertisement, if you do more advertisement, then you will get more customers. That's what it says. So what we write is, we are very certain that distributing more flyers will increase the number of customers. Okay. And it says that we can conclude that flyer did influence the number of customers. So that's it. Now task 2, upload TV restaurants data. The data represent weekly profit in thousands for 20 restaurants. 10 with TV, 10 without TV. Management wants to see if the new TV sets increase the profit. Okay. Here, since the management wants to see if the new TV sets increase the profit, we are trying to compare the average profit between restaurants with TV and restaurants without TV, and try to see whether the restaurants with TV has increased in profit or not. So that's the case of one-tailed t-test. I have uploaded that TV restaurants data, and column A shows the profit of TV, restaurants without TV, and column B is for restaurants with TV. Okay. Now before p-value by one-sided t-test, we need to check the average and see whether our assumption is backed by average is or not. So restaurants with TV, its average is 7.5, and restaurants without TV, its average is 9.5. Okay, so here you can clearly see that restaurants without TV has more profit than restaurants with TV. So our assumption is not backed by the average. Okay, so we shouldn't compute, right? The question is not necessary since p-value should not be computed. Why? Before performing one-sided t-test, we must first check if the actual averages are in agreement with the claim. Here the claim is if the new TV increases the profit. So that's it. So here also p-value, since the assumption is not backed by p-value, so we don't have anything. Okay. So one line conclusion, we cannot, that's all. So test is inconclusive. All right. Now let's go for task 3. Upload soda in schools data. The school district compared two schools, one that serves soda drinks for lunch and one that doesn't. They collected the weight of the students and wanted to see if there is any statistical difference in their weights. We are trying to see if there is any statistical difference in the weights of the students in these two schools where they serve soda and where they don't. So this is the case of two-tailed t-test, since we are just trying to see the statistical significance of the average. Okay, statistical significance in difference of average. Okay, what is the p-value? Uploaded the sodas and school data, so let's go for two-tailed t-test equals t-test. First array is soda, second array is without soda, comma 2, comma 3. So that's 0.2457, which is 24.5%. p-value greater than 5%. Okay, what we have written is, since p-value is very large, greater than 5%, so we cannot conclude that there is a significant difference between the average weight of the students in those two schools. Okay, so what is one line conclusion? We do not have. Okay, so we do not have enough evidence that the average weight of the students are significantly different between those two schools. Okay, upload hospital data. A hospital is trying to implement a new patient check-in procedure. It is known that for this particular hospital, the average waiting time for patient is 45 minutes. Your job is to determine if this new procedure provides significantly shorter waiting time. Okay, new patient check-in procedure will help lessen the waiting time. So I would go for one-tailed t-test, since we want to see if this new procedure did some good job. Okay. Oh no, this is a bit tricky. So we are clearly asked question related to average, but we do not have the second data to compare to. Let's see if we do have second data or not. Okay, here I have uploaded the hospital's data and there is just single column of data, waiting time for those 25 patients. Why we can't use t-test is, since we do not have a way to come up with two subgroups of this data, so that's why we can't use t-test. Okay, now here this t-test, we cannot perform t-test for this type of problem when we are asked to compare one data set and its average to a particular number. We use a procedure called confidence interval. So please read this properly. When we are asked to compare one data set, okay, this is one data set, and compare its average to a particular number. Average of this is 34.24, and we want to compare this average to a particular number, that's 45 minutes. Okay, so that's why we always use confidence interval. So please note this down. Okay, look at the procedure below and on how to answer task 4. So compute the average and standard deviation of the data. Okay, let's do that quickly. So average, you can see that average is 34.24 and standard deviation is given by equals STDEV. The array is 30 up to 25, so that's 14.11. we have done the step 1. Compute the margin of error. Okay, margin of error is simply equals confidence dot t alpha standard deviation size. Okay, what is alpha? Alpha is 5%, that is 0.05. okay, that is 0.05. Standard deviation, we have already computed that, which is 14.11, and size is the total number of rows, okay, which is 25 data points. So alpha is similar to p-value. Okay, that's what it is saying. Okay, by letting alpha equals to 5%, we are constructing 95% confidence interval. Okay, since 100% minus alpha, which is 5%, is 95%. Okay, in statistics, 95% confident means that's quite enough. Okay, sometimes we might want to go for 99% confidence interval. That's fine, but 95% confidence is good. Okay, and that's acceptable. Okay, so alpha equals to 0.05 in this case. So let us go for confidence equals, so that's margin of error. Margin of error, let me write ME. So equals confidence dot t, that's 0.05, that's alpha. Standard deviation is 14.11, comma 25 is the total number of data. Okay, so margin of error is 5.824. okay, margin of error is 5.824, and construction of the confidence interval is, the left endpoint of interval is average minus margin of error, the right endpoint of the interval is average plus margin of error, which can be written as, so confidence interval, let me write this as CI, so that's average, so equals average is 34.24 minus 5.82, so that's left endpoint 28.42, and the right endpoint is equals 34.24 plus 5.82, that's the right endpoint, that's 40.06. okay, so which we got 28.42 and 40.06. That's fine. Statistical interpretation is, since the confidence interval is below old average of 45 minutes, we can now with 95% confidence claim that the new average is below 45 minutes. Okay, since confidence interval is below 45 minutes. Okay, which is 28 up to 40. Conclusion: yes, we can confidently claim that the new procedure lowered the average waiting time. That's it. In nutshell, the confidence interval tells us that the average waiting time for new check-in procedure is somewhere between 28.42 minutes and 40.06 minutes, and we can be 95% confident that this is correct. Comment: in most statistical applications, we are satisfied with 95% confidence interval, that is alpha equals 0.05. However, one can always compute 99% or 99.9% confidence interval. Just let alpha equals 0.01 or alpha equals 0.001. So p-value, we have calculated margin of error. What is one-line statistical interpretation? We can simply say that we are 95% confident. Okay, and so one-line confusion is the new method. Now let us continue with hypothesis testing discussion. Now this is a comparison of this textbook that we are using in LIMES and the standard textbook that usually any other introductory statistical course uses. Okay, and here why we are using this approach is proved in this way. Okay, so here our approach, the way that we have studied about hypothesis testing, is way easier than what normally other students learn in introductory stat class, right? So here I think this might be the first time that you might have been hearing this word hypothesis testing, okay, which we didn't use. Okay, now the main essence of hypothesis testing is just to figure out the p-value and try to interpret it in efficient way. So that's it. Okay, and what does the standard textbook or the classic textbook does is that they usually go for null hypothesis, that is represented by HO, and alternative as hypothesis. Okay, so it is quite confusing to make anyone clear about what is null hypothesis and alternative hypothesis. But in our textbook we haven't done that. We have simply discussed about the p-values and tried to work with a regression, t-test, one-tailed and two-tailed, and confidence interval. And also confidence interval, we will be talking about this much more in next lecture. Okay, a keen reader might have noticed nowhere in the text thus far did we use the word hypothesis. This is strange since vast majority of standard textbook contains numerous chapters devoted exclusively to hypothesis testing, and here we do not even use the word why. An example will help. Remember an earlier example regarding the soda data. Okay, sodas in school. I think that's somewhere here. Yeah. Okay. And the school district compared two schools, that one that serves soda drinks for lunch and one that doesn't. They collected the weight for students and wanted to see if there is any statistical difference in their weight. Given the data, your job is to perform the appropriate statistical test or procedure to help them decide. So it was quite straightforward that we went for comparing two averages, okay, between schools. One of the school provided soda, another didn't. Okay, so that was quite straightforward, and we got the p-value which was quite higher, and we said that the averages are we can't say that the averages are different. Okay, so that was the decision. But what the standard textbook does is, the task is to perform appropriate test is almost never asked. Instead, the students are told which type of test to apply. Okay, either regression, t-test, or confidence interval. Now, in a real practical world, or you are never told to apply which kind of test to use. Okay, but our textbook allowed us, our discussions allowed us to choose between various tests like regression, t-test, or confidence interval. Okay, so it is unlikely that the school district will specifically ask for t-test in this situation. An appropriate null hypothesis is formed. Formal hypothesis is never formulated. So null hypothesis means the usual assumption. Okay, the means for two population averages are equal. Okay, the averages for two populations, two schools are equal. That's what it supposes. Okay, so stating hypothesis, null hypothesis is mathematical correct, but it is very confusing for almost all students, and even many so almost all students have difficulty in understanding a null hypothesis. Okay, so our two-sided t-test is performed. Okay, and p-value is obtained. Both does the same thing. Okay, now statistical interpretation. Since we did this thing, since the p-value is too large, we cannot claim that there is a significant difference between the averages weight of the schools. That was what we found out. Okay, now in classic textbook, what they write as statistical interpretation is, since p-value is too large, we cannot reject the null hypothesis. Now here it says that we cannot reject the null hypothesis, so that's too confusing. Okay, it is too confusing since we have two negative connotations. Okay, so cannot reject, these are two negative. Okay, that's double negative, so which is quite confusing. And conclusion, we concluded that we cannot claim that the two averages are different. Okay, but in standard textbook they write we cannot claim that two averages are different, cannot claim that two averages are different. So the conclusion we got is same in both cases. Okay, so the hardest and in many ways the only problem is to identify the correct statistical treatment. In this case it was t-test. Okay, The question is, in our studies we found out that once the student correctly picks the procedure, 80 to 90% of them manage to finish the test flawlessly and offer the correct conclusion in our case. But when we go for formal hypothesis testing procedure, it is mathematically correct, but it is quite convoluted and unnecessary at this introductory level. How convoluted? Well, the following quite common example from a standard textbook will help make my case. Okay, example: the management of a store introduced a new checkout procedure and wants to see if the sales increased. Okay, if the sales increased, we collect the data and formulate the null hypothesis, but due to mathematical reasons, the hypothesis must be formulated in a such a way that we stipulate the sales did not change. Imagine that we performed t-test and got a high p-value 0.22. Below is the mathematically correct conclusion in standard textbook. The p-value is too high. We cannot reject the null hypothesis that the cell did not change. So cannot reject and did not change. So these are three triple negative logical nightmare. It says that. Okay, so it's quite confusing to see those three negative sounding things. Okay, triple negative, because cannot is 1, reject is 2, and the statement did not change is the third negative. And believe it or not, the above example and the conclusion is not uncommon. One can easily pick any standard statistical textbook and find many examples that follow the exact scenario above. Okay, no wonder the student have hard time understanding the t-test. It is our experience that at this level it is counterproductive to introduce formal hypothesis testing routine. Okay, so that's why we didn't go for formal hypothesis testing. It will juggle behind those negative connotations and it will make us confused. So that's why we didn't introduce null hypothesis and the formal hypothesis testing. But our job is quite easily performed by using the p-values, which is actually the similar kind of process, and we got the same result, right? So that's all.